Okay, so we're now being recorded. Anyway, I just wanted to thank everybody for being here. We've got this afternoon we have the panel on islands and stuff, much of the stuff we discussed today. The rules of engagement are as they were before. Basically, the panelists each get about 5 minutes to speak. To try not to interrupt them unless you really have to, and then we'll have the free for all with questions. So let's let the panelists say their pieces. And Marika is kindly agreed to be a neutral moderator, and so I will shut up and join the rest of the crowd right now.
You didn't say I had to be neutral, actually, but there we go.
Well, okay,
well,
do your best.
Okay, so thank you, everyone. So I think we're going to take the panelists in alphabetical order. So it would be Ahmed who's going to start with his presentation. So I pass over to him.
Okay, great. So let me share my screen. You guys see my screen?
Yep.
Yes.
It's blank, but we can see it.
Oops, that's the wrong. Yeah, okay, here. Okay. So my comments are going to be about the firewall paradox in the setup that I discussed, and what the role of the islands is in the story. So here's the eternal black hole. We know that if you compute the semi-classical entropy of the radiation outside on both sides, it just keeps increasing for all time. But for unitarity, as I reviewed, it needs to saturate to the coarse-grained entropy. The claim is that this has a firewall paradox. You can run the amps argument. So after the page time, you require that the entropy saturates. It should not increase anymore. So let's say we're somewhere around this blue regime here. What this means is that the mode B that escapes the black hole must not increase the radiation, must not increase the entropy. Therefore, it can only be entangled with the radiation. However, the vacuum at the horizon requires maximal entanglement between A and B, right? The usual semi-classical state is an entangled state between the outgoing Hawking modes and the ingoing Hawking modes. And the proposal from AMPS is that in order to have unitarity, you need to break this entanglement. So somehow at the page time, say somewhere here, the entanglement is broken and a firewall is created. Okay? So the statement is that the standard firewall argument applies to this case. However, it's a bit more dramatic in this case, actually. The reason being is this situation has a boost symmetry. And due to the boost symmetry, there was nothing special about that point that I picked over here to say that the firewall was created here. In fact, you are led to the conclusion that the firewall is everywhere along the horizon. Hence why I call this the eternal firewall. And but now with islands, the story seems to be different. I'll explain why seemingly here is bolded in a second. So in the island story, there's no contradiction with there being entanglement between B and A and B and the radiation, because A is a subsystem of the radiation. That's what the island does for you, using ideas of subregion duality and so on, and also the explicit computation of the entropy was not in conflict with A being entangled with B. So this buildup of entanglement realizes, the emergence of the islands due to the buildup of entanglement realizes ER equals EPR, and also previous ideas of Papadodimas and Raju and the Fernandez and others. Let me make a quick comment about this bolded seemingly. The reason why I said this is because I was led to this conclusion because I said that in the entropy computation, we saw that we can use the semi-classical state, right? And that's what all of this is based on. But there should be a more fine-grained measure of actually probing whether this entanglement is there or whether there's a large stress tensor here at the horizon or not. In particular, it should ultimately be settled by the path integral. You should follow the following 2 steps. First, you should define the operator that measures this entanglement or the stress tensor at the horizon, and then simply compute its expectation value using the full path integral and see what the full path integral gives you. And then the hope would be that if this computation is dominated by the semi-classical saddle, then we would say that the semi-classical state is what is felt by an observer that passes through the horizon, and then we declare victory. But this more careful calculation, I don't think has been done yet. I think it's kind of difficult defining the operator that measures things at the horizon in a gauge invariant way, and so on and so forth. And I think that's all I had. Thank you.
Okay, thank you very much. So we're going to postpone questions until each of the panelists has given their presentations. So next, I think it is Juan who's going to continue.
Okay, so I think I'd like to give a sort of some very general remarks on this island discussion. So first, let's start with a certain comment, which is what one can call a central hypothesis or central dogma of black hole physics, which is that the black hole as seen from the outside can be described as a quantum system with s degrees of freedom, and it evolves unitarily as seen from outside. Now, these degrees of freedom are not manifest in the gravity description, and part of the discussion is, well, how to make them manifest. Sorry. So that, for example, fastball are an attempt at a more explicit description. I should emphasize that these are some degrees of freedom which describe the black hole as seen from the outside. So the hypothesis is that for any experiment that you do outside, arbitrarily complicated experiment, you can describe the results of those experiments by replacing the black hole and whatever physics associated, whatever calculation you do associated to the black hole by this finite number of quantum degrees of freedom. But I think a central question is how much of the interior these degrees of freedom describe. And so there are 3 options, which are that they describe all of the interior, they could describe part of the interior, or none of the interior. Okay. Now, we should not be fooled by our language. So when we say that these degrees of freedom are inside, our language presupposes an answer to the previous question. But it's in principle not obvious. It's not an obvious question, because the degrees of freedom in the central dogma, in the central hypothesis, are the ones that suffice for describing every experiment from the point of view of the outside. It's not obvious at all that those degrees of freedom have anything to do with the interior. Okay. But recent developments strongly suggest that the correct answer is that is the middle one, that they describe part of the interior. So the idea is that the degrees of freedom describe everything that is inside the entanglement wedge. And how big is the entanglement wedge depends on the circumstances. So it can differ for different black holes, for different interior geometries. And so, for example, for a black hole early through its evolution, the entanglement wedge could be this green region that covers a big portion of the interior. For a black hole after the page time, then as Ahmed and friends have shown, and Planington, it describes only a small region of the black hole, and most of the interior is not described by these degrees of freedom that describe the black hole. Now you can ask, what is describing these other degrees of freedom? Well, it's the radiation. Okay, I think that's, and I think some part of the recent discussions on how to apply this and so on is not to distinguish well the sort of degrees of freedom that appear here in the interior of the black hole, and we can call them black. So when we talk about the degrees of freedom that live on a spatial slice here, and we can call them the black hole degrees of freedom because they're inside. but they should not be confused with the black hole degrees of freedom that appear in the central hypothesis, the degrees of freedom that describe the black hole as seen from the outside. Those later degrees of freedom only describe this, only describe the green region. And well, I guess as it was said many times, the solutions to the AMPS paradox and so on rely on the fact that the entangled pair is one pair is in the green region and one pair is in the blue region at late times of the modes near the horizon. Okay, thank you.
Okay, thank you very much. So Samir, I think, is the next speaker. Do we have Samir? No, somehow he's not online. So Steve, oh no, he is here. Okay, great.
So is my screen up there now?
It is visible, yeah.
Full screen. Okay, good. So can you see the pointer as well as the screen?
Yes, we can see it, yeah.
Okay, so what I thought I would do is summarize what I understand from the picture of the computations which have been done with JT gravity and associated things. And I just simplified the picture to make it something that I could extract something from. And so let me just make very cryptic statements about what I think has been said. And then others could tell me if that's correct. Okay, so let me begin by asking, suppose you do a Gibbons-Hawking type of computation. So there you have time made Euclidean with some period beta, but the Euclidean metric just ends outside R equals to M, actually just ends at R equals to M. And then you do this calculation of computing Z, and from that you can extract something which you might call the entropy. But of course, if you have a consistent theory of gravity, then you should find that many states in the gravity theory. And the problem always has been that the answer which you get from the Gibbons-Hawking calculation is always some finite number, just comes from the gravity action. And that's not the number which matches what you get from the actual calculation with the Lorentzian black hole metric. So here on the bottom right, I have drawn the usual problem with the bags of gold or the Hawking radiation situation in the Lorentzian section. So if you make the black hole by collapsing a shell, there's a singularity, we are in Ellington-Finkelstein coordinates, then at any late time t, depending on how late there is, you can make a very, very long slice, and then you can keep putting many and many quanta on it with zero total energy. If you just look at the Hawking paradox, you're throwing in matter and letting it radiate at the same rate. So then you actually create this kind of a slice. And then you get actually infinitely many states. And because you get infinitely many states, the actual partition function for that particular mass in the actual theory of gravity is infinite. So it doesn't match up with this value. So in fact, the mismatch between these is the paradox. You can call it the bag of gold problem or the information paradox, but this mismatch is the problem. So one of my first questions to, which I don't understand about what's being done in the recent work, is I absolutely agree that if you're doing a Gibbons-Hawking calculation, Gibbons-Hawking would also agree that they should certainly go to higher loops and higher handles and so on. So you should certainly do that when you talk of the Gibbons-Hawking answer. But the Gibbons-Hawking answer will always be some finite value by its very nature. But the puzzle you're trying to solve is that the Gibbons-Hawking answer is not what you actually get from the Lorentzian section. So one of the questions I'd like to then maybe ask the panel again later on is, if you find the finiteness of Gibbons-Hawking entropy or do something with it, has it taught us anything at all? Are we even asking the right question? And so JT gravity is also a simple model, just 2D gravity. So I expect to have the same mismatch between the two sections. So just go to the next page. So of course, we should now go to a Lorentzian continuation and see what the recent work say about that. So clearly, they're not just looking at real beta, they would take beta to beta plus IT. But then again, the question is, if we are simply analytically continuing the Gibbons-Hawking amplitude or answer for some correlation function, can we get anything new which we didn't already know in the Euclidean calculation? And at first, it seems to agree with what I would have expected. You don't get anything novel in terms of the information paradox, because you simply get the normal Lorentzian picture, which you get by analytical continuation of the Euclidean black hole to the Lorentzian black hole. And also all the radiation quanta and their entanglement and everything looks to be exactly the same thing that we had in the original calculations of Hawking. So I just taken this picture from one of, I think, Almeri and Juan et al.'s paper. And so the quanta going outside, I just labeled them B, and their entangled partners C, which are going inside, are exactly as before. So up to there, it looks to me exactly like what we had before. And that's not in contradiction with anything I know, because we just analytically continued the Euclidean black hole. So then I think we define this generalized entropy, which for any surface is the area part plus the entanglement across it. And that's fine. You can define this for motivations from Ryu-Takanagi's extensions, and you can study its evolution. But let me not worry about those motivations, but just focus on what I see the final answer is that people seem to have gotten out of it. And in the original black hole problem, the entanglement entropy of the radiation itself, it grows for a while, at some point starts becoming bigger than the Beckstein entropy. That's when you actually have the problem. And then the entanglement keeps growing, for the eternal hole can keep feeding it, letting it evaporate, and S(n) of R just grows without bound. But these arguments have suggested us that at the point when it actually starts becoming more than S Bekenstein, we should change our definition of what we call the entanglement entropy of radiation, and somehow make it look more like as entanglement of what is in the radiation region and what's in the island region. So I just wrote it as R union I. And as the black hole area becomes small, the area term becomes ignorable. In the old picture, or the standard picture, the entanglement was all between the B and the C. And the whole problem was that the B was getting more and more entangled with the C. But if we somehow change our definition for what we are asking about, and we say, no, we'll ask about B union C, or the island union R as the set, and its entanglement of that with everything else, then of course this will obviously decrease. So in some sense, from what I see, and this is my confusion, so far we actually haven't done anything, made any change to the original problem from 30 years ago. We've just redefined what we want to call the entropy of the radiation. And then of course, this is the Page curve. If you take R union I, it will go down, but that's just what Page was saying anyway. It doesn't, so solving the problem, we just redefined it. So of course, perhaps we shouldn't stop here, but I just written here the fact, if we stop here, then we seem to have not solved anything, but just try to define it away by saying, instead of entanglement of R, let's talk about entanglement of R union I. But that, if we just stopped here, of course, the problem would be what happens when the black hole evaporates away, because this was just a change of definition. So we haven't done anything. But when we start asking the physics question, what happens when the black hole evaporates away, we'll have to ask what happened to the quanta C. So we need to postulate some dynamics to get the information out. And so let's look at the kind of computations I see in various papers, which might give us an answer to that. So papers of Saad and Shankar et al. And so on. I'm just trying to extract some rough picture, which I seem to have gotten from there. So if we have Lorentzian evolution of, let's say, two systems, which are, let's say, very far from each other, I'm making a very toy model of what I understood from those papers. You can't actually make wormholes in the Lorentzian section without destroying the light cones. So for a while, we can let it go Euclidean and then back to Lorentzian. And then while it's Euclidean, then you can actually connect things by a wormhole. And let's see what the effect of that wormhole could be. So Euclidean wormhole, just as we do in handles in string theory, could be written as a sum over operators, which you can expand if the wormhole is long to leading order, just have the identity, which doesn't do anything. But then the lowest field you have, and suppose the fields on the two sides were just a scalar field for concreteness, then in fact, when you expand the operators, somewhere in the lowest dimension operators you expand, you will get a term where you could maybe annihilate a scalar field quanta here and create it over there. Okay, so now at least we are saying, okay, there's an interaction. We do want to get the stuff from inside to outside. And if this is indeed what you people would like to say, then is this what you're saying, that there's some interaction, a non-local one, which will pick up a quantum from inside the hole and somehow place it outside the hole? So maybe I'll just phrase it as a question. Is this the final model, maybe expressed in very brief terms, that the quanta C that fall into the black hole, which are the members of the entangled pairs that go in, they move out through a traversable wormhole and get out to infinity. And that's being proposed as a solution. So, okay, so these are my questions. I just want to understand if this is all that has actually been being said in these papers. And at the bottom, I've just written down what I think my perspective is and what should be the correct solution. With first balls in the Lorentzian section, you just get these balls, they're horizon-sized objects. They all have the data like a star has. If you put them in a one-loop path integral and do the saddle point of that Euclidean path integral, then you get the usual saddle point. But the Lorentzian states that contribute to it are actually these. And in my opinion, the ER equals EPR actually doesn't work. It's only if you keep low energy gravity alone, it seems that you have the standard diagram, which has a horizon and the other side as well, and seems to suggest ER equals EPR. But I think there's some very beautiful physics going on here, just like when you had the Seiberg-Witten theory or the conifold transition. At some point, new degrees of freedom descend down and solve paradoxes that seem to be arising. So I think all these fuzzball configurations are degrees of freedom that descend upon you when you're just about to make a horizon. And that actually disallows these kinds of surfaces like the Einstein-Rosen bridge. Just as I was trying to mention in my talk, it actually makes them higher energy. And in fact, you can only get, if your asymptotic mass is m on each side, you can only get these things which are not actually physically joined, and you never actually create a horizon. So anyway, that's my perspective of what I think that string theory is telling me. But I'd be very interested to learn if what I was saying in these slides here is actually what's being said, because my concerns, again, to summarize, are just two. If we just stop at this stage here, it seems that we just have the same picture that we had 30 years ago, and we have the same problem that Paige had pointed out, except we're just redefining the problem by saying that for some motivations we got from Ryutakanagi and so on, instead of looking at entanglement radiation, we look at entanglement radiation union the island. But that doesn't tell us what happens if the black hole evaporates away, because then we really will have a problem at that stage. But then if you try to make a physical model of what happens when the black hole evaporates, to me it seems that this is the best we can come to if we assume that the horizon still creates entangled pairs to the leading order in the way that Hawking wanted. The moment you keep that, which let's say is the opposite of the fuzzball, where you say you will not create entangled pairs in the usual way. So if you still want the entangled pairs in the usual way to happen at the horizon, then if I follow everything else, this is the only picture which seems to fit what I'm seeing. And I would like to maybe ask the other panelists if I have understood this correctly. Thank you.
Okay, thank you very much. I'm sure there'll be responses to that, but let's go on to the fourth discussion, which is by Steve. You need to unmute yourself, Steve.
Yeah, so can you, Samir, can you unshare your screen? So and then I'll share mine. Good, so let's see, what do I have to do? And let me make this. Okay. So, Marika, can everybody hear me? And you can see my slides?
We can see the slides and we can hear you. Yeah, thanks.
Okay. So I'm going to talk about some of certainly comments that resonate with what's been said. And I want to just ask a question. What should a complete bulk description of quantum gravity contain? We think we have a boundary description in gauge gravity duality. If the duality is precise, the bulk description should contain exactly the same information. Let me talk about outside the black hole quantities to make life simple. Well, it's clear you need fine-grained microstate information. You need the energy eigenvalues of the boundary Hamiltonian coded into the bulk. Here's what we think a spectrum of a black hole looks like. This is from our favorite toy black hole, the SYK model. This is something we call the spectral form factor at late time. If you don't do any averaging, it looks like this erratic red curve that codes this funny, chaotic random matrix behavior of the energy eigenvalues. A correlation function will look very much the same. So there are simple observables that at late time are infected by this, as Juan pointed out. So you need to know this stuff. You also need to know about eigenstates. You need these for correlation functions. And you would need them seriously to compute like the individual matrix elements of the density matrix of the radiation, all kinds of other things. So you certainly need this information to have a complete bulk description. So what else should this bulk description contain? Well, it has to contain in some way horizons, Einstein-Rosen bridges, and space-time wormholes. These geometrical structures obviously play a role, a central role in any bulk dynamics. So we need them. So then the question is, what is the relation between these two things that we want? Are these horizons, Einstein-Rosen bridges, and space-time wormholes effective emergent properties of underlying microstate structure. The idea that horizons might be emergent from fuzzballs, I think, is what Samir has called fuzzball complementarity. And I guess it's related to the Vicro hypothesis, but I'm afraid I have not studied that. Is the Einstein-Rosen bridge a consequence, an emergent consequence of entanglement, EPR? Tensor networks are kind of a picture that visualizes that and makes it kind of concrete. Are space-time wormholes, are they just a diagonal sum over fuzzball orbits? This is a space-time wormhole. These are some caricature, some cartoon of some kind of fuzzball orbit. When you average, this gets glued together in a way that Phil talked about earlier today. Or are these geometric structures equally fundamental? Perhaps they're gauge equivalent to microstate information. This is a point of view that Marolf and Maxfield have discussed recently. We would say that the Einstein-Rosen bridge is the same as entanglement. They're identified. Or this space-time wormhole we call the cylinder, it's the same as this diagonal sum by some gauge invariance, some identification. So when we give a microstate description, are we just working at a particular gauge we could call fuzzball gauge? Well, here's an analogy that we've been pondering that's basically due to Harlow and Jafferis. This is a terrible slide, I apologize. So it's an analogy on the boundary, and that's all we can do right now. So consider two decoupled copies of this SYK model, call them left and right, with fixed couplings, no ensemble averaging, no fancy stuff. Well, the complete set of microscopic degrees of freedom are the fermions in the left theory and the fermions in the right theory. The two sectors, left and right, are manifestly decoupled. This is the kind of setup you'd use to study the spectral form factor. Now, we could multiply the path integral by 1 in the usual by introducing auxiliary fields. We'll call them sigma left right and G left right. We could add the following coupling to the action. I sigma times G minus psi psi. Now you integrate over sigma and you get a delta function enforcing this left-right field equals psi left, psi right. This is like this diagonal sum equals the cylinder. So but then you can integrate over G again. You have a delta function, it just clicks and you get 1. All you've done is introduced a factor of 1. So you might imagine a big description where you keep psi left, psi right, and G left right, and sigma left right. And that obviously forms a redundant description to overload a word that Nati Seiberg likes to use to describe gauge theories. But if we compute certain things, like the time average spectral form factor, or a purity that goes into computing the page curve, then G left right and sigma left right too comes to life. And it has a vev. The variable is auxiliary, but it's there if you need it. And this is the analog of a space-time wormhole. So in the purity case, it's not G left right, it's GAB, where these are replica indices. This is a replica wormhole. Okay, well, this is a boundary construction, but maybe possibly there's something in the bulk. You need these auxiliary fields, some huge redundant description. So geometry is there if you need it, and the microstates are there if you need them. Well, that's all I have to say, so I'll stop sharing my screen and entertain any questions. I guess all of us will entertain questions.
Okay, what I suggest first of all is that Juan and Ahmed respond to Samir's question, because I think it was a clearly posed question for them. And in the meantime, indeed, if people kind of put their hands up, or also if people want to use the chat, they can do so to draw attention to questions. So Juan, do you want to take on Samir's question?
Well, I mean, I think that, I mean, part of the question is whether, I mean, I think part of what Samir was saying is, well, okay, you're doing a redefinition of what you mean by entropy, and with the new definition, the interior is somehow counted in as the entropy of the outside, right? But one has not shown how to extract that information from the inside to the outside. But I think that the idea is that when you do complex enough operations on the outside, you will be able to extract this information. And the work of the Stanford group, so Steve and friends, have shown how to do that in the context of a simplified model. So the fact that in the leading semi-classical approximation, the information looks like it is inside the black hole does not mean that it's inaccessible for the radiation, for someone who does very complicated computations on the radiation. I think that's a point. I mean, the entropy. I mean, you can view the computation of the fine-grained entropy as a special kind of computation of the outside. It's some computation that can be done purely on the outside, and one finds that there is some interior contribution. So the interior, even though it's inside the black hole, it gives some contribution to this fine-grained entropy, according to the standard rules of gravity. So I think the new aspect is that the standard rules of gravity, including non-perturbative contribution, wormholes, and so on, ensure that this happens. So it's not something that is being done by fiat, but it's derived from the rules of gravity.
So can I ask, in the description you're giving is very much semi-classical, so you're working with gravity and then quantum fields on the curved background. If we were going to try and phrase the discussion of islands in the language of, say, a worldsheet description of a black hole, can you give a sense of what the islands would be? I appreciate that involves another step, which is understanding how to identify a horizon in a worldsheet description of a black hole. But do you have any thoughts on that?
By a worldsheet description of a black hole, I assume you mean treating a black hole in the full string theory?
Exactly.
As exact conformal field theory?
Yes.
Well, I don't know. I think, I think in the full string theory, maybe the endpoints of the island are not very well defined, or maybe they have some fuzziness and so on. But in these situations that Ahmed discussed, the islands are very, very large, larger compared to the size of the black hole. So I would expect that the qualitative aspects will be similar, but the details of how to find it and so on will be more complicated. I mean, there is a certain miracle that happens in Einstein gravity, which is that the computation of these Renyi entropies, which involve non-trivial topologies and so on, boils down to a computation involving the original geometry, right? It's somewhat similar. Well, it is somewhat related to the area formula for black hole entropy. So you do some computation, then you get a very simple geometric formula. And yeah, so how that would work in string theory, we don't know.
Okay. So Ahmed, did you want to also take on Samir's question? I have another couple of, so people are indeed using the chat, and I'll read out the questions, but maybe Ahmed, you also wanted to comment on Samir's question.
I didn't have anything else to add to what Juan said.
Okay, great. So a question really for Juan, and I guess for Ahmed too. Let me read it out. If one accepts that only a part of the degrees of freedom that are supposed to describe the black hole lie in the interior of the black hole, what principle makes them geometric? To be more precise, to remove the firewall, one required maximal entanglement between exterior and just the interior, just inside the interior degrees to be of a geometric kind. Raphael, I know you're in the line as well, just to say, so I'll pass to you next. So that was the question. So let me say it again. If one accepts that only a part of the degrees of freedom that are supposed to describe the black hole lie in the interior of the black hole, what is the principle that makes these geometric? And that was a question really for Juan in particular, but also I guess Ahmed.
I think that there are degrees of freedom. I didn't understand the question very well, because there are two things we can call the black hole degrees of freedom. So one is the degrees of freedom that appear in what I was calling the central hypothesis or central dogma, right? Which are the degrees of freedom necessary to describe the black hole as seen from the outside, right? And then there are the degrees of freedom that appear in the semi-classical description, which might be inside the black hole, right? Both of these could be called black hole degrees of freedom, but it was crucial not to confuse the two. And the question, I think, well, the question, it seems from the question it was confused, or at least it was confusing my understanding of the question.
Yeah, I think you're right, that the question comes from not quite understanding what you were explaining, which, okay, I think I did. Raphael, did you want to go next? So you wanted to ask a question, you got your hand up.
Okay, let's see, let me just be polite and appear. Here we go. Yeah, I just wanted to comment on the fact that I feel like there's actually a middle ground between some of the skepticism that people have expressed and some of the claims that are perhaps not, well, caricatures of claims where we say we've completely resolved the paradox. I don't think anybody's really claiming that. And I would describe it as follows. I think there's really something magical about the gravitational path integral. It's an approximation, presumably. We don't know what it's an approximation to, and we don't know how good it is, but it does things that no classical theory normally knows how to do, like compute an entropy a la Gibbons-Hawking without knowing the microscopic degrees of freedom. And I think the recent developments are genuinely a breakthrough in the sense that for the first time, we're able to compute the page curve and demonstrate unitarity from a gravity calculation. I don't think it's a particularly controlled gravity calculation, but it does give the right answer. And that, I think, is really a qualitatively new thing that had to do with recognizing that the gravitational path integral receives contributions from these islands. These are not new things. In some sense, they were always in the quantum Ryu-Takayanagi prescription. It just hadn't been recognized that non-trivial ones appear. And the paper by Pennington and by the other group first pointed these things out. But I think, on the other hand, for example, Samir is correct in pointing out that there is kind of a disconnect between saying, on the one hand, this Hawking radiation is mixed because I just drew a picture that showed Hawking's calculation. And on the other hand, I'm going to say the entropy is 0 because I'm going to include the interior in what I call the entropy of the exterior. And I don't think that's really a contradiction because it isn't a controlled approximation. The calculation didn't have to give you consistent answers in this respect. And for this reason, I don't think the firewall paradox has been resolved. I think if you assert that the Hawking radiation is pure, then the arguments that the horizon can't be smooth are still upheld. But I think it's interesting that there exists one context in which this contradiction does not arise, which is the one where the most precise calculations have been done, and that's SYK-JT duality, where you can understand the discrepancy by saying this is really an ensemble of boundary theories, each one of which is unitary. Then the ensemble outstate is a mixed state. You're averaging over different outstates produced by different theories, but the ensemble average of the entropy is 0, and the gravitational path integral simply computes the ensemble average in both cases.
Could I ask a clarification on what Raphael just said? And maybe the question is also to the other panelists. If I actually do the calculation using replicas for the entanglement entropy of the part outside, which we call R, with, let's say, the part I, will I get anything different from what I knew how to do before? So let me say what the two methods are. In the earlier days, there are many calculations, the CGHS model. I've also done some with my student Keski Vakuri, where you actually evolve the physical state up in the Schrodinger wave functional, and you actually compute the entanglement of one side with the other. You get a number, and of course, the number just keeps going up. Now, if you do it by the replica method, you actually compute the entanglement of just the outside part, SR with SI, with the rest, the R part with the rest. Won't you get exactly the same answer? Because the calculation, there are just two ways, there are multiple ways of computing the entanglement of one segment with another segment when the whole thing is in a particular state. It's a very well-defined question. You can go to the Euclidean section and do it by replicas, or you can go to the Lorentzian section, compute it some other way, like was done in the old days. So it seems to me even the calculation, the answer of the calculation now done through replicas is the same as the answer as before. This is what I would like to check. I think the answer is exactly the same. The motivation from the Ryu-Takayanagi and so on is to say that instead of looking at S of R, just look at S of R union I at late times. Is this wrong? Is the calculation of the entanglement of two segments on that big Penrose diagram, is the answer for that entanglement itself different if you say I want entanglement of this with this? And if so, I didn't actually understand how that comes out of what we have put in.
I think it is different because you're not simply saying, let me just randomly include the entropy in the interior of the black hole. That would kind of like, I mean, a lot of people who were sort of defending Hawking's calculation in the early days were saying, hey, look, globally the state is pure if I just include the interior and the exterior, so why are you guys so worried about the loss of unitarity? That's not what's being done here. What's being done is you specify some data far away, and then you do a gravitational path integral in which you fill in the bulk entirely, and there are different contributions coming to that, and you have no choice but to include all of the ones that appear. So I think it's controlled. I think the key breakthrough is to not ask the question that Hawking asked. I don't think we've found Hawking's mistake in that calculation. It's to ask not what is the outstate, but to ask directly, what is the entropy as computed through the replica trick, and then do that calculation. And then gravity is kind enough to spit out the answer that we like. And in that calculation, you have no choice but to include these interiors. So it's not a random thing that you do at that point.
But the picture is the
Raphael,
same. Penrose diagram drawn is
Raphael,
the same.
can I ask a quick clarification? You said the calculation's not controlled. Do you think the page curve will have large uncontrolled corrections? Or are you talking about other quantities?
No, what I mean is just that, I mean, of course, I believe that the page curve, well, so for example, in ADCFT, from the boundary point of view, we have long thought we know how to calculate something like that, or at least in principle. And so I don't doubt that the page curve has the shape that we think it does.
No, I mean the bulk calculation of the page curve. Do you think there are large corrections to it that we didn't include?
No.
Okay,
Just as in Gibbons-Hawking, I don't think that they got the answer wrong for the entropy of a black hole. They did get the answer right. I just don't know why.
Okay, you know, in that sense, you mean it's uncontrolled.
It's in that sense that we now can compute the page curve, and I don't know why. I mean, there's some amazing things that GR does for us that go beyond what a classical theory normally can do when you just stick it in a path integral.
Okay, thank you for the clarification.
It's as a co-host, I'm not allowed to put my hand up, it would seem, but I'd like to make a comment at some point. Is it okay if I make a comment?
A question in the chat, right?
Yeah, I asked the chat, but I want to actually expand a little bit. Right. I think my concern, and I think Samir's concern a little bit, is that what we're seeing is yet another repackaging of an old problem that we had an old formulation of. So just let's broaden the discussion. The firewall, for example, looks like a repackaging of the old conundrum. Do we use the whole infalling vacuum, or do we use the Boole-Ware vacuum? Because the Boole-Ware vacuum looks just like a firewall. And so if you want to save unitarity of quantum gravity or Hawking radiation, you use the Boole-Ware vacuum and it'll be unitary. You just went up with a firewall or some completely ridiculous quantum state at the horizon. That's a repackaging of an old problem. And what I'm worried about is we're seeing the same thing happen again. We're saying we want to save quantum gravity, or we want to save unitarity in quantum mechanics. And we knew 30 years ago that there's all these Hawking quanta sitting on a space-like hypersurface. I'm going to call that the old island. The 30-year-old island is all the Hawking quanta sitting on a Cauchy surface inside the black hole. And we know that if you want to get the right answer, you want to get the page curve, you've got to include those quanta in the calculation of the entropy, if you want to do that. The neat new thing, to some extent, is perhaps that you found a way to formulate that using a Ru-Taki-Yanagi kind of calculation inside Euclidean quantum gravity, but still, you really haven't answered the problem. You've just repackaged all that old problem into a new thing. I can see Jan's shaking his head, but it looks to me like it's a repackaging.
Just because gravity gave you the answer that you expected doesn't mean you should be suspicious.
No, but I'm saying that, okay, what's the difference between what I call the old island, which is all the Hawking quanta on a Cauchy surface inside the black hole, and the new island? Is there any difference?
I would like to make a comment about...
Can I hear from the answer from the panelists first, and then come back?
Go ahead, Juan. I mean, you want to answer.
I think that this new island first of all, has been derived from the rules of gravity, and is telling us a qualitatively new thing, which is that the degrees of freedom that are inside the black hole should be viewed as part of radiation. Let me say this in a slightly more provocative way. So you're working on the fastballs, right?
Of course.
So the idea is that there should be some fastball that describes the black holes, and to describe the interior, you need another fastball. You need the interior fastballs, and so you'll have some interior fastball glued together with in the way that Steve was discussing, with the exterior fastball that you've been thinking about. I think that's...
We never put a fuzzball in the interior, but I have sympathy with some of the things Steve was saying. That's another angle we can go into, but there's no interior from my perspective. There's just the fuzzball.
That's right. That would be this fastball that describes the black hole as seen from the outside. And I think following the ideas of Steve and so on, we would have another fastball. There would be a fastball that you start from radiation and it describes an interior with some rugged structure.
Oh.
And then when you glue the two types of fastballs that you would have found, you would get
I could believe there's a coherent sum along the lines of what Steve said. That
yes,
exactly what you're saying.
Yes,
so,
but I think something crucial, and I think the new thing is that there is this separate interior fastball that you would build out of the radiation degrees of freedom. I think that's a new thing. So it's that
I'm resistant to the term interior fuzzball. That strikes me as an oxymoron.
But why would you knit the interior fuzzball? So why would you knit interior fuzzball?
Well, to describe the experience of this interior, people who are in the interior. So, but it depends for what. So it depends for what. So if you want to describe the black hole as seen from the outside, you don't need it. But if you want to describe some qubit or some observer that is in the interior of the black hole, then you would probably need it.
So for you, I think this sort of links to the question I asked earlier. So you still draw in your diagram a horizon, because I think most of us here would agree that to all effective purposes, there is something that looks like a horizon, right? It has the characteristic features. But I think the difference between what Costas is saying, that you have one fuzzball, and what you're saying that you have two distinct, is really, it's really the notion there's a horizon, right? The notion of behind or in front of is really actually having a horizon. Yeah. So in your calculation, where do you see that there's really a sharp horizon, as opposed to a very typical black hole microstate that almost looks like it has a horizon? If something approaches it, it experiences a geometry which is very, very close to what you have in the black hole. How do you distinguish between the difference between those?
That was a question for whom?
That's a question for you. I mean, it's a question for, because I think we, okay, there will be different perspectives on fuzzballs here, but the things that people work with in supergravity are clearly very atypical, right? They're near extremal. They don't have the features of a typical black hole, right? So the actual, I mean, something, a more general version of the fuzzball proposal would be that there's, that there is structure that's what you would call behind, but there's not a sharp horizon there, right? And I don't see that that's particularly different operationally from what you're doing. I mean, you put the line in the diagram and we can all agree that, an observer which is going close to that region is experiencing the kind of, distortions and so on that they see with the black hole horizon. What's the difference from this?
If I can make a comment.
Yeah.
So we're trying to sort of answer the question of what does a space-time look like? What is it, what does an observer traveling in the space-time see? In these pictures that we were drawing of space-times, I don't think that's the interpretation that we meant when we drew these pictures, at least in my talk. These pictures are supposed to represent a calculation. So for example, when you complete the entropy calculation, you find that it reduces to a prescription in some semi-classical space-time. And so we draw the semi-classical space-time and we apply the rules and so on. But if you want to ask, say, what does an observer measure as they pass through the horizon? Okay, now there's an operator that measures that. You go ahead and so perform the computation, write down the expectation value of that operator and the path integral, and then see what the path integral gives you. It might give you the semi-classical approximation, and then you would draw the semi-classical spacetime with a smooth horizon, or it might give you something else. And maybe it might give you a nice spacetime that has a firewall just behind the horizon. I don't know. But I just wanted to stress that in a lot of the spacetime pictures, at least I was drawing, these should be thought of as results of sort of, they're representative of certain computations.
Okay.
Can I make a comment on I guess Nick's question? I'd be really curious to know what of the older calculations exactly you have in mind, because it seems to me that there are some genuinely new calculational ingredients in what has been done. For example, the existence of a non-trivial quantum extremal surface, where you have to look at the variation of the generalized entropy. You have to check that it's stationary. You have to check that it dominates over the trivial one. This was an insight in these papers that I was not aware was even in the repertoire of questions that we would have asked 20 years ago. So I think that's not the issue. I think the issue is when we overinterpret the picture that, as Ahmed emphasizes, this is just a calculation. And the pictures that appear in this calculation should not be confused with the space-time that an infalling observer, for example, would see when they fall through it. Any more than we would say that in the Gibbons-Hawking calculation, because they got the coarse-grained entropy right, the world is really Euclidean. It's a calculation. It's a thing that you can do with gravity, and it gives you the answer that seems to be right. And I don't think we completely understand yet why.
Just want to respond to that very briefly, because I see 3 people have got hands up and I should shut up. But basically, I agree, there's a non-trivial and interesting calculation here. So what's happened is that they've taken the old story, and by injecting a little bit of our knowledge of holography, the Ryu-Takenagi kind of formula, this new calculation, it's sort of forced us into a corner where we say, okay, we want to preserve unitarity, but it's then told us as an outcome that we have to include the entanglement of the interior states with the exterior. And it's obviously the outcome of that calculation. I think it's intrinsically interesting, but I think it's much less than what we're being told it is. It's simply telling us that we have to do what we knew we had to do 30 years ago. And it's coming out of a calculation, which I think makes it cool and interesting, but I don't think it's anyway, it's a step towards understanding what's going on, but I don't think it's a solution. I'm going to shut up because I see 3 or 4 people in line.
So let's go next to Raghu, actually. So,
Yeah.
so Ahmed, you answer, and then let's go to Raghu after that.
Okay, just a quick comment about what Nick just said. It's the space-time picture, just to emphasize my previous point, the space-time picture is not the result of the calculation, it's a representation of the calculation. I think these are 2 different things.
Could I just make a comment on that before we go to the other question, just to close off this part of the discussion? I think what is worrying me is that what we call the calculation or the new calculation, I want to ask, isn't it just the Gibbons-Hawking done with, let's say, more handles added? And I'm very happy that somebody could do such a thing, assuming that's what it is. It's the Gibbons-Hawking, which they did at leading order. You can add more handles, and that's more difficult. And suppose you can do that, and let's assume you can do that. But the whole Gibbons-Hawking answer done and then analytically continued, I thought had no more information than the Gibbons-Hawking originally before analytic continuation. But knowing the Gibbons-Hawking answer and that's a finite number actually doesn't take me anywhere towards the information puzzle, because that is the puzzle. The Gibbons-Hawking always gives a finite answer. So what I wanted to ask was, when people say we have a new calculation, we have a result, is the result sort of analogous to just doing Gibbons-Hawking, but not just for the disk geometry, but disk plus a handle, or maybe more handles? If that's what it is, it's still not taking us anywhere towards the information question, because the question is the mismatch between the finiteness of the Gibbons-Hawking and the unbounded nature of how much you can store inside the Lorentzian horizon. So, okay, I'm just repeating my question, but I'll let anybody who wants can respond to that.
Yeah,
I think it's a different question, right?
Yeah,
You're computing the
RT
fine-grained
formula,
entropy.
I mean, the RT formula is morally the same as Gibbons-Hawking, in the sense that it computes for us a fine-grained entropy, but without telling us what the microstates are. So it doesn't tell us explicitly what they are. You're complaining about that, and you're quite right to complain about that. but it gives us a new answer. The information is in the answer it gives us. It taught us something new about how we should view about the interior, I think. And well, of course, it gave us the answer for the page curve using Gibbons-Hawking-like methods. It's not identical, but it's the same method in spirit.
Okay, shall we move to Raghu's question? Because I know he's had his hand up for a while.
Sorry,
So,
I just wanted to comment on Nick's earlier question about the old island versus the new island. I think there is information here, which is the location of the island. Like it's not at some arbitrary point. Like, so earlier we had no claim that it has to be 3 Planck radii behind the horizon or central charge times the Planck radii. So that is an output of the calculation. It tells you how much of the interior you have to include in the correct calculation. So that's like a quantitative input, which is new.
okay.
That's all I wanted to say.
Yeah, I think that's a good point, and I think it's
And I would certainly agree with that. I think that's a reasonable.
Stam, do you want to go next? I can see your hand up.
Yes, I'd like, in fact, I have a question in this context, whether, coming to what Nick was referring to, whether one of the new ingredients at least would be the point that was made this morning during Ahmed's talk, that when one actually does smooth out the cusp between where the page curve, where the island contribution is, whether the new ingredient is the fact that whereas up to now, when one was calculating the Renyi entropies, the implicitly or even explicitly, the framework was the replica symmetry approach, whereas now apparently it's possible to actually describe quantitatively replica symmetry breaking, and it is this replica symmetry breaking that can lead, in fact, to the description of new correlation between the islands that were not, that could not have been taken into account in the previous calculation. It's actually a question more than I'd be glad to find what people think about.
So any comments from the panel? Juan, Ahmed?
I think the replica symmetry, the solutions without replica symmetry were important, as Ahmed said, and well, Steve found in his papers, when you, to smooth out the curve, but they don't seem to have a fundamental importance in
But don't they describe also correlation between islands? And therefore contribute to the wormhole configurations?
I think that, I mean, replica symmetry has not been shown to have a qualitative importance in this problem.
No, but the way it's broken, whether the way the replica symmetry isn't sufficient, of course, but whether once one takes into account how it's broken, that whether that can lead to something new.
Well, in principle, it could, but it is not part of the story, of the recent story.
Oh, I see. Okay.
Emil, I guess the next question from you.
Yeah, I wanted to re-ask a question I asked this morning to the broader panel. So the crude picture we used to have of what black holes were in ADS was that you had some thermal state of, say gluons in n=4 Yang mils. And so, there was an idea of, UV-IR correspondence where it was sort of the low energy degrees of freedom of the gauge theory that are describing things in the middle of ADS. So, so we have, say some number times n squared of degrees of freedom that are describing the states of a black hole. So now it seems to be that we're saying, okay, well, now we want to couple the system to a radiation bath. And what's being said with the incorporation of the island is that there's sort of two places where the usual CFT degrees of freedom interact with the auxiliary system. One is at the boundary where you're explicitly coupling the CFT to the radiation system. And the other seems to be where the RT surface is, where the island is intersecting with some causal wedge of the CFT. So it seems like the coupling at the boundary is one where I'm just coupling some explicit low energy fields of gravity to some explicit low energy radiation degrees of freedom in the bath. The other interaction seems to be much more subtle, because it seems to be an interaction of the n squared degrees of freedom that I would have thought would be describing the black hole with some large number of degrees of freedom of the radiation system. And it seems to me that coupling has to be kind of strong in order to account for fast scrambling and the Hayden-Preskel effect, where I send in a quantum and it comes back out immediately. And Juan is shaking his head, so maybe he can tell me what's wrong with that picture.
Well, I think that the fact that the space-time is connected through the entanglement wedge does not mean there is an interaction. It just means there is entanglement between the degrees of freedom of the field theory and the degrees of freedom in this radiation far away. So,
but doesn't that get me into Samir's problem, that if there's entanglement but no interaction, how do I actually transfer bits out from
yeah, if there is no interaction, you cannot transfer anything through the surface. It's like, I think the clearest example is the eternal black hole, right? If there is no interaction between the two black holes, you cannot transfer information, even though you can have something very, very close on one side or the other side of the horizon, you cannot send a signal. Once you include interaction between the two, then you can send a signal. Sort of.
You can think of the teleportation story as starting with the eternal black hole, where the two boundaries cannot talk to each other. But then if you turn on the double trace deformation for teleportation, what that does is that it moves the location of the quantum extremal surface slightly, so that information can go from one side to the other.
So you're saying it's sufficient for me to have large entanglement, but the weak interaction at the boundary, and that's enough to do the job?
It's enough to move the location of the quantum extremal surface and do the job, yes.
Okay, thank you.
So I can see some hands up, but I'm going to go to a question in the chat because we haven't heard so much from Steve. So this is really asking him to talk a little bit more about his ideas about having two SYK models. Specific question is, if there's no ensemble averaging, why is there no factorization? But maybe as part of the answer, Steve kind of wants to talk a little bit more about how his model might work. Do we still have Steve?
Yes, I'm here.
Yeah, good.
Well, yeah, part of the point, and this I'm just echoing what I think Phil talked about earlier today when I was asleep, that when you don't have any explicit interaction and no averaging, you will have factorization. And so the question is, does that mean, let's say that things like these space-time wormholes, if we work in some Euclidean signature, are just wrong? They need to be ruled out? Or does it mean that they're there, but there are a lot of other things that combine with the space-time wormhole and allow the thing to factorize? And these pictures that are being developed recently, this nice picture of Maralth and Maxfield, this periodic orbit story, would somehow say that there's the space-time wormhole, but there's also all kinds of other stuff that seems tied perhaps to microstate information. And that you add all that stuff up and the thing factorizes. But then if you average, what happens is all that other stuff, we sometimes call it the off-diagonal contributions, averages away. And you're left with a space-time wormhole. And so if you want some kind of bulk description, now, so then there's this question of language, and I'm not sure if it's language or if it's contentful or if it's, well, I'm not sure what it is, but you might imagine some kind of description where the wormhole, which is coded in this SYK model as this G left right field, is just there. You decide to add it into the description, and it is redundant. It's just sitting there, but it's available to you if you need it. Let's say you do some averaging or some, you're computing some Rennie entropy. All of a sudden, that field, instead of being auxiliary, as auxiliary fields can do, it comes to life. It says, I'd like to have a VEV, and that's the good description. So in a complete description, the wormhole wouldn't be the only thing, but it might be lying around there. So when you do one of these calculations we've been talking about, it's there to dominate the path integral. Well, okay, I could go on too long, but let me stop there.
Can I just ask for a clarification on what you just said, Steve?
Yes,
so
please.
These wormholes, could you use them just to continue with what Juan had said a little while ago? When you normally burn a piece of coal and get radiation out in ordinary StatMech, you can't actually take the radiation and do something with it to extract data which is still inside the coal. But with the black hole, the idea was, yes, there are entangled pairs outside and inside, but if you do appropriate things with the quanta far away, these wormholes can actually make you extract stuff so it's different from the piece of coal in that way. Is that also what you would say the wormholes you're talking about can do? I'm just trying to separate formalism and definition from the physics, some non-local physics that we are trying to isolate here.
I think, roughly speaking, I think the answer is kind of yes. I'm not sure I've answered, I understood the language exactly. The thing we don't have in the piece of coal is we don't have this nice other description in terms of gravity. All we've got, if you will, is the boundary description. It seems that somehow in gauge gravity duality, there is this dual description in terms of things we call gravity, in terms of geometry. And there's a way that it can mock up is not right. There's a way that it can be equivalent to certain things happening in the boundary description. Now, simple geometry, by that I mean the, eternal black hole and things like that, probably is not enough, at least in my view, to describe everything you can compute on the boundary. Like that erratic red curve, like that knows about the detailed energy eigenvalues. Maybe if you do geometry and you soup it up enough, as in the fuzzball, the very fancy fuzzball calculations, you can do that. But the simple garden variety geometry that Gibbons and Hawking would talk about, for instance, probably won't be enough. But if you compute the right thing, it might be that's all you need. So the question is, you have this big toolkit in the big description. The bulk description contains all kinds of stuff, fuzzballs, but also wormholes and other things. I'm not sure if those wormholes are effective descriptions of the other stuff or if they just are rendition. If they are like auxiliary fields compared to the other stuff, or if they are like gauge relatives, as Maralf and Maxwell would say, but they're lying around at your disposal. And if you ask the right question, and we've learned recently that the page curve is one of those questions, all that other crap kind of gets averaged away. Maybe to briefly echo off what Raphael said, if you consider that you have an ensemble of quantum systems, like we understand JT gravity to be, you can ask a question, how important it is to do that ensemble averaging? That is, if we took one representative on the ensemble, would you get almost the same answer? In the late time spectral form factor, I showed you a picture. The average thing was that nice smooth blue curve. The non-average thing was that erratic red curve. The answer is there's a big difference. There's a big change, representative to representative of the ensemble. In the page curve, we're in the happy situation, it's what we call self-averaging in condensed matter physics. One representative of the ensemble gives almost the same answer as a full average would. So all the other things that a detailed description of one quantum system contains somehow average away. And so that might be why the gravitational path integral is so effective there. It gives quantitatively almost certainly the right answer. All the other things that might be stored in there microstate geometries and stuff are not important for that quantity. To compute the erratic red curve, you'll need stuff like that. And for certain questions about transferring information out, it might be that geometry is enough. To know detailed things like the individual matrix elements of the density matrix, you will need this more fine-grained information. Now, I'll stop there. I've gone on too long. Sorry.
Thank you very much, though. Shall we move on to a question by Edgar? Because I'm aware he's had his hand up for a while. Edgar.
Hi, yeah, thanks. I think when my hand went up, I wanted to appease some concerns, but I think they've been sufficiently appeased. So maybe I'll amplify a concern, which is basically Raphael's, which is, the way to understand the new thing in these calculations is if you assume the Euclidean gravity path integral, that's a big if, then these results come out. Now, the question is that we don't fully understand the Euclidean gravity path integral. And one way, for example, Andy Strominger complained about this is, I'm sort of paraphrasing, but he basically said, look, you child, in the past, anytime we use the Euclidean gravity path integral, we had some other way originally of understanding the answer that it was giving us. And in this situation, the very first calculation was using the crutch of Euclidean gravity. So I'm just amplifying the concern that we should think harder, and I think a lot of people are thinking harder about, I guess what people are calling nowadays the unreasonable efficacy of the Euclidean gravity path integral.
Thank you. Anyone want to respond to that? I guess no. Andrea, I guess you also have a hand up for a while.
Yes, I would like to get some clarification on the statement that the pitch curve computation from the islands gives a unitary evolution. And I'm asking because you could imagine some simple qubit models of black hole evaporation where for, let's say, the first half of the evaporation, you emit a la Hawking with Hawking pairs. And then for the second half of the evaporation, you emit the partners of the original Hawking particle that went out into the early radiation. And in that way, the final state of radiation will be pure. So you go from pure to pure, but the information of the original state has never come out. And so I'm wondering that without having sort of a specific mechanism that maybe descends or has to descend from a more UV picture, can we actually say that this new computation gives unitary evolution as opposed to showing the final state is just pure?
I mean, it produces evolution, an evolution of the entropy that is consistent with unitarity. We have by no means sort of written down all of the matrix elements of the S matrix of a black hole. I think that's the statement so far.
But then in simple models, if you can mock up an evolution that goes from pure to pure, where in the second half you emit exactly the partners of the early radiation, it seems to me kind of in the spirit of this calculation that you that this wormhole connects to whatever purifies the early radiation, and so in this simple model, nothing of the original state has come out. So I'm just wondering.
The difference is in the models you are describing, you're doing that by hand. In the models that we are describing, gravity is doing that. And if gravity wants to do something, we let it do it.
Okay. So there was a question in the chat a while back, which I think is probably very straightforward for Ahmed and one to answer. I think you answer it in the papers, really. So this is about, can the island configuration say anything about entangled systems without a horizon? So, are there situations where islands would be relevant there?
Juan considered de Sitter, so I'll let him talk about this.
Exactly.
Yeah, I think the islands have to be behind the horizon. So, so in general, yeah, so because otherwise, if it wasn't behind the horizon, then that information would be accessible from some other region. And that other region, you would be able to, I mean, yeah, it wouldn't be part of the region you originally considered. That's the short answer. Now, in some cases, it looks like it is outside the horizon, but once you decouple the systems, then it will be behind the horizon of the decoupled system. Yeah.
Okay. Stefano has his hand up, and he also had a question in the chat. So Stefano.
Yeah, thank you. I just wanted to ask that question in the chat. So a quick clarification about the dual model that you mentioned, both Kwan and Ahmed mentioned in their talks. In that case, you have a 2D CFT living in the auxiliary system, so in the flat system, coupled to a quantum mechanics, which is dual to the JT gravity system. My question was only, how do you describe in that context the 2D CFT living in the ADS system? Is that where is that encoded?
You mean using that picture?
Yeah, like in that picture where you have a quantum mechanics coupled to the flat space CFT, where is in that picture the ADS CFT, the CFT living in the ADS?
In the models that we studied, we never said anything too precise about what that quantum mechanical system is and how it's coupled to the flat space CFT. It was just a cartoon for intuition. But the thing that we studied mainly was this ADS, this hybrid ADS flat space regions, or theory, with CFT living throughout with transparent boundary conditions. So, yeah, we didn't analyze in too much detail what this quantum mechanical picture that you're describing would be for this situation.
But just, yeah, that's right. But it has to be a little more concrete. Imagine the CFT which has 3 fermions, right? So then the idea is that the quantum mechanics theory has to have an operator of dimension 1/2, an approximately conformal operator of dimension 1/2 that doesn't, that to a certain extent in the larger limit doesn't interact too much with other operators. That's the idea.
Thank you.
Okay, so
Nick had some... raise my hand about the evaporation. So okay, I make a black hole by collapsing a shell of supercomputers, and but what's going on at the end? Because again, all the stuff which is inside, just from the start, from collapsing the shell of supercomputers to make the black confusion. And I didn't. Samir asked the same question, and
Juan, can you?
Yeah, I will show. Can you see this? Yeah. So the statement. So let me just answer. So here, if we look at some late times, we have blue rectangle here near null infinity. That's the region of where the radiation lives. Okay. So the interior continues to exist in the past, right? So here in this blue region, in the interior, the idea is that this blue region is in the entanglement wedge of this information that is in the interior. That's the idea.
But the interior is not, okay.
The sense that it is gone in the sense that here, if you look at the top part, so the dotted line is some sphere around the original black hole of fixed size. And then this, then you have this R equal to 0 and an empty flat space. Space like separated relative to the other region and yeah.
So Juan, is this like
this is really an extrapolation of the picture that we see here on the left-hand side.
Is this like a remnant/baby universe scenario? Could I say that the quanta that fell into the black hole together with the information inside gets locked up in a little remnant, which then disconnects into a baby universe? So you don't see it in the original space-time, which just has flat space over there. You have the radiation, but there is a baby universe somewhere else. And then you have little wormholes connecting you to that baby universe with which you can do non-local interactions to get stuff out from there if you really want it. Is that one way of putting it?
Yes, I think that's right. Yeah.
Okay. So Nick also wanted to come in, but actually with a slight, I think, change of theme, right? Going back to what was being discussed with Steve.
I wanted to try and, so in the interest of sort of trying to build bridges between the two sort of camps here a little bit, because every time Steve starts talking about this, I begin to sort of see patterns in the kinds of things I do. So in the interest of that, I want to just discuss what I think about boundary states. And in particular, when I say boundary states, I think about the fuzzball. The fuzzball is a very complicated state. And I could easily imagine that somebody falling in or the universe has some kind of image in that state. So for example, when I go to my bathroom mirror, I see another universe on the other side. Now that universe is incredibly limited by the fact that there's one state for my bathroom mirror, but a very complicated mirror with a very complicated set of states could produce an image that looks like it's completely independent of what's happening in my side of the mirror. And so, my thinking here is very much influenced by John Cardy and his work on boundary conformal field theories. With a considerably complicated boundary state, if you want to calculate correlation functions, say 2-point functions here, I can do it by calculating 4-point functions in a doubled universe where I factorize on the appropriate boundary channel that goes through the boundary state. So I could easily imagine that a fuzzball could produce something that looks just like an eternal black hole or a wormhole or anything else, in the same way that a suitably complicated bathroom mirror could create the appearance of a totally independent connected universe. So my question really is to Steve, would that be the kind of thinking that you were having when you were talking about, taking combinations of fuzzballs? I hope Steve hasn't left.
No, he's watching you.
I'm just trying. I'm not sure. I think is the short answer. I'm not sure. I think
my paradigm is really literally the Cardy calculation of a boundary correlation function in the presence of a boundary, and the smartest way to do that is to calculate a 4-point function factorized on the right channel.
Yeah. I mean, I'm a little bit, well, I'm not sure if that's the analogy. It might be the right analogy. I just don't know. I think the kind of idea is yes, that you might in some way be able to see, an Einstein-Rosen bridge or a space-time wormhole as an emergent sort of structure that is made out of microscopic information.
Yeah, that's exactly.
Might be effective, and it's hard for me to translate that into a conformal field theory. That could that could possibly be the case, and I think in some of these SYK descriptions, that's kind of what happens. You have two manifestly decoupled systems built out of fermions. And, if there are a large enough number of fermions and you do the right thing, these collective fields, which represent average descriptions, have VEVs, and that's like a geometry forming.
Right.
And I think, for me, one of the questions is, does that mean that you forget about the Einstein-Rosen bridge? Do you forget about the space-time wormhole, that was never a good idea? You should banish them from the theory? That seems like
no, I'm not saying that. In
wasteful.
Fact, the first thing you learn in electromagnetism is the smartest way to calculate the field of electric charge in the presence of a grounded surface is to use the image.
Yeah, I guess that I have to think about that analogy, but I think the question for me is, well, maybe let me phrase it as a question for people that work on fuzzballs. Suppose that fuzzballs don't have horizons, and suppose you try to describe the Einstein-Rosen bridge as some entangled set of fuzzball geometries, maybe like one of the final pictures in Samir's presentation today. How do you derive, and I don't want to let you use the boundary, just from the bulk, just from geometry, that you get the eternal black hole, that sum over ragged geometries produces a horizon? Is it that the average somehow of geometries with no horizon produces a horizon? How does that work in the bulk? I'm not going to let you use boundaries and talk about thermalization and stuff. There should just be a calculation just using geometrical or whatever you want to add in the bulk. Long strings, brains, whatever tools you think is a bulk description, and show that you get an effective horizon.
Sure. But I think that
would be the challenge.
I think Samir has a partial, but I should hand over to Samir, but that sounds much like what fuzzball complementarity was trying to do.
Well, yes, exactly. So this is a question of trying to give a bulk derivation of fuzzball complementarity. Not saying, oh, these states thermalize and therefore there must be a horizon, but just saying at the level of geometry, if you average over a lot of these microstate things, you get a horizon. You have a bunch of geometries without a horizon, but far away, they look kind of like a black hole. And if you do something to a large collection of those geometries, a horizon forms. I believe that is the statement. And how do you do it?
I don't think you form a horizon, at least from the extremal supersymmetric solutions. I don't think there's any horizon formed. But again,
yeah, maybe the extremal ones are particularly difficult to handle. I would like to have some highly non-extremal ones when you get around to producing those.
Yeah,
right.
And average those and show that those make a horizon.
But I think that's a central issue, I think, Steve, right? That the ones that you're looking at are so non-representative that they're not showing the feature that you want to get. And I think that is the big question of the program.
Now let me just make a brief comment. On the other hand, I think there are things that are not reproduced by a smooth horizon. There's no way that erratic red curve, something outside the horizon, doesn't involve falling through the horizon or difficult things to understand. There's no way that can be produced by a smooth horizon.
Yep.
You know, and so you need something else. Now, I think if you average correctly, it might be that aspects of that can be produced by smooth geometries, these space-time wormholes, and maybe other fancies.
We have done that.
What?
We have computed, for example, in a supersymmetric microstate geometry, we have computed a 4-point function, and then you see exactly that you have basically a dip, and then you basically have a ramp, and then you have oscillations. Now, that's a very specific geometry which we are using. This is in a paper which we wrote with Nick last year. And you can see it very nicely how information comes out. Now, it's a supersymmetric solution, so the information doesn't come out after an exponential time, but after a polynomial time over the n1 times n5.
Yeah. So
we have done that. This is done. And it comes out very
it's not done because you haven't done it in the non-extremal case where the gaps are exponentially small, and you can see that the average thing is described by something with a horizon. Okay, that's what you need. You need to show that.
In the extremal case, there's also left moving temperature, and you can also argue that there's a horizon describing thermalization and so on and so forth. I think my feeling is that it's much easier if people who do arguments, which are I think it's much easier for people who do arguments about non-extremal black holes to try to push them towards extremal ones. And to make and to give something to calculate rather than us building non-extremal microstates, because this will not happen, and they'll be very non-generic. For extremal ones at this point, we are really in a good slot. I mean, we have a lot of them. They have really the nice features which we expect from a typical microstate. We know how to sum. We discussed on Monday the discussion session. One can even be able to do sums over geometries, and not averages, just adding geometries quantum mechanically, and then taking expectation value in those. So for extremal ones, you can do a huge amount of things. And the question is, I think it's much easier to try to think about.
So can you find the space-time wormhole?
Why would I find a wormhole?
Because we think a correlation function, if you average in time, is described by a space-time wormhole. The ramp is described by a space-time wormhole. Can you find it?
Why would it be okay? This is something which I don't understand. Why would it be a wormhole and not something which just decays forever? Why don't you get just the black hole result if you average?
Because there is a small correction to the one horizon result.
Yes, but but the wormhole only exists in the non-extremal case. I don't think in the extremal case there is a wormhole.
Well, I want you to be in some place where you can find a wormhole.
I'm not sure.
That's the challenge.
I'm not sure. Find besides the wormhole. I don't know.
Joseph, maybe we should let Samir say something about black hole complementarity in this context, or not.
I was just making a small comment on the discussion that Nick and Steve were having. Yes, so when you make these approximations to try to get effective behavior, which could, for some purposes look like a horizon or the other side of the black hole, I think what fuzzball complementarity says is that you can only do it for observations with energies bigger than t. So when you look at the Hawking quanta, which has E of the order of t, you could never actually get any replacement for the fuzzballs in any sense, which will reproduce the traditional horizon, because the moment that horizon can reproduce physics of the Hawking energy quanta E of the order of t, you'll be exactly back in the production of entangled pairs, and then the small correction theorem tells you that any small changes there cannot get your entanglement away. So you have to look at appropriate things, maybe in form of high energy quanta, and then it can be approximated for the things like the ones you're asking. And for Nick's analogy, for example, if I have a mirror there and I try to put an image charge on the other side, well, I can't look for things. There's always some imperfection in the mirror at the electronic scale, which has the data of the mirror. And so to that extent, even though we idealize it as a uniform charge, it's not a uniform charge, right? So if you start looking at, only when you start looking at things which are more than a few atomic spacings averaged, those quantities can be reproduced by this. So I think the point is you will never actually get the horizon for the purposes of actually saying the physics around the horizon can be like the physics in this room. It's only for certain observations that you can possibly get the wormhole or this, but they're not the kind of objects for which you can ask the Hawking question. That's all.
Let me just make a comment. Suppose, let me just formulate a question that I believe we all should be able to answer, which is what the 2-point function of simple operators far outside the horizon of a black hole behaves like as a function of time. Okay, this is something that everybody that is involved in understanding black holes, let's say in gauge gravity duality in particular, should be able to answer. I mean, a complete understanding would require an answer to that question.
Right.
Now we believe, and this is something that Phil Sod worked out in detail, if you compute that correlation function, at early time, it's given by the standard stuff that Veronica Hubany and Gary Horowitz taught us by quasi-normal modes of a horizon. At late time, it is something like that erratic red curve. And if you average in time, so you're studying very long time things, which might be low energy, I'm not sure about the energy, you should find something that's described by a space-time wormhole attached to a disk. That gives the correct picture of that ramp region. The plateau is something more complicated, which we can discuss later. And so the question is, why is that simple geometrical description contained in a fuzzball story for that long time averaged correlator? Why does it work? Why is geometry unreasonably effective?
Here, this is the answer. This is the
yeah, but why is that the same as a space-time wormhole?
It's not a wormhole, so you get the same black hole result. So basically, if you compare a BTZ and the fuzzball.
Yeah, but it should be the same as a space-time wormhole. Why is it the same?
There's no wormhole, it's extremal. So you can reproduce exactly. So the point is, in the D1D5 CFT, you know very well everything. You can do 2-point functions, you can do everything. And you can compare the 2-point functions you compute in a fuzzball with the ones you compute in the CFT, and you get the result on the nose. So so this is the result. I mean, there's a perfect decay, and then, okay, this is a very special fuzzball, and the information comes out almost entirely from the cap. In a more generic one, it will not come out from the cap. And if you look at the sum of fuzzballs, at some coherent superposition of them, you'll get some stuff here, which is going to be, you'll get something in this region, which is going to be of the type of stuff what you want. This is what you get from averaging these geometries. But each and every geometry,
whoa. I think Steve,
coming out.
Joseph, I think Steve is actually asking us to do that average over geometries, which we do not know how to do at this point.
If you want density matrix, we do know how to do it, but it doesn't help too much with the geometries we have. If you want a sum over a coherent superposition of microstates, that we cannot do yet, indeed.
That's exactly the point.
Standardis had some ideas about
well, it's fine, but I think that's exactly Steve's point. That's what we need to be doing.
Can I make a very simple comment?
Yep.
So I want to sort of move the discussion from horizons to just space-time in general. Okay, I didn't start this out simple, but you can consider in these studies of islands and so on, you can consider the case where you have just an extremal black hole, so just pure ADS2, you have an infinite throat, glued to this flat space region.
At infinity.
At infinity. This very simple setup also has an island. You can compute, for example, the entropy of the radiation of the flat space region. In 1+1 dimensions, this thing has an IR divergence. But the way that the thing that saves you is that there's an island starting from the extremal horizon and goes up the throat. But when you compute the entropy of the radiation in the flat space region, it becomes the entropy of the union of the flat space region plus some region that goes all the way down the throat. And that's how you cut off the IR divergence. And so what this would be suggesting maybe is that if you have sort of ADS2 microstates,
which you have,
if you look at each one by itself, then the space-time ends somewhere. But if you entangle it with the faraway region, this entangled superposition will somehow generate the sort of the remainder of the IR region down the throat.
Oh, very good, very good, very good. That's something which, I mean, in principle, I mean, all the geometries which we build, one can actually do them flat space with an ADS2. So one can actually build them in flat space with an ADS2 throat, which goes on forever. And then, so the gluing with flat space and the I mean, we can build on the microstates. But what I don't understand is, I mean, just the calculation to see this island coming up. But maybe we can talk about it in more private. But this is really, I mean, this is really a good idea. I mean, if I mean, we have all the geometries, so it's a pity not to use them. But somehow the point which I want to make is that I mean, for me it's much easier people who make arguments and so on. I mean, if they try to generalize stuff and push stuff to understand what's happening in the extremal case, I know it's maybe not so fun. I know maybe you cannot fall through the horizon drinking your coffee. I know that there's all sorts of garbage happening because you are supersymmetric. But it's much easier to move those arguments into the extremal land and try to use what we have right now to get some physics out and to make some cool connections, rather than, I mean, for us it will be another 5 years until we can get anything non-extremal, maybe less. I mean, Nick has €2.5 million to hire postdocs and to do these things. So we have quite a bit of resources. Europe is very kind, and we are basically we have a big factory going, but still it's quite a bit of, I mean, I think you can get much more physics if people can move their non-extremal arguments to extremal arguments rather than wait for us to.
I think actually we have a chance of doing near extreme or near future, but that's another story. Do you think we should? Oh, David's got his hand. Oh, sorry.
Yes. Can I just jump in with a quick follow-up question for Juan? Juan, would you mind resharing that slide you had a moment ago with the final state after the black hole had completely evaporated?
Yeah.
Thanks. So I'm just trying to piece together in this, on the right-hand side, in this final picture. So the state, if I consider a partial Cauchy slice at late times, and I'm interested in the state of this radiation which has been produced by the black hole, then what we heard from today is that the fine-grained gravitational entanglement entropy of this region is essentially 0. Yeah. And at the same time, there's a large entanglement between the degrees of freedom in this region and what remains inside the black hole in this causally disconnected region. And also, there's no direct interaction between these two regions. So just piecing all these together, and my question is, are we supposed to think of the state on this partial Cauchy slice at late times as a pure state or an entangled state?
Okay, so this state has a sort of semi-classical description. Yeah. Let me see. This is a diagram, right? Giving some, if you wish, some approximation to the state. Okay. Mm-hmm. In this approximation, the state, well, there is some geometry and so on. And if you only look at the part of the geometry that is in the right rectangle, right, it will be a mixed state. So the quantum fields in this description are mixed in the right rectangle. Mm-hmm. Okay. Now, in principle, there is a full exact description in the, if you did the full quantum gravity path integral, as Ahmed was saying, if you sum over all geometries and you do the exact computation, that will give you a state in the right rectangle that would be pure. Okay. The statement is that at least for the purposes of computing the entropy, you can get the actual value of the entropy in that right rectangle for the exact state by doing a computation on this approximate state. Okay. And the computation you have to do in this approximate state is to include islands and include the interior as a big island, right? So the quantum extremal surface would be at the vertex where, so at this vertex here, right?
Yeah.
It looks like you're saying that the Cauchy slice somehow splits in two at some point and leaves part of itself behind.
Yeah, you have a piece here and another piece here.
What's going on at that point? Is that not a remnant issue? Is there not a remnant issue at that point?
Well, you could imagine this, I mean, as Samir said, you could imagine this as a baby universe that went out here. You can consider this red region here some kind of baby universe that was disconnected from the first. All we are saying is that when we do the RT, the Ruta-Kanagi proposal for this kind of situation, we get zero entropy here for the region outside. If we apply that, which is what we expect.
Because if we did the calculation that you and Kurt did, and Samir and Sumit did 25 years ago, you would have said, "Oh no, the final state is a pure state. It's not mixed with anything. It's not entangled with anything else, right? You threw in some quanta, they split into left movers and right movers, and then they came back out, and nothing's entangled with anything else. The radiation state's pure. So how is this different?"
Well, that computation would have to be compared with the exact gravity computation after you sum over all geometries. We don't know how to do that computation in gravity directly. It's related to what Steve was asking about, the 2-point function of long times and the erratic behavior, blah, blah, blah. But if one could do that computation, then one would get that pure state. The business with ADS-IF to duality and so on is to replace the whole region that is behind this dotted purple curve. So we replace this whole region by some degrees of freedom. Some could be a field theory or the left and right movers and blah, 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 and all that, right? In that description, there isn't anything here, right? And we never talk about doing the path integral involving the geometries here and so on. We just have some exterior interacting with degrees of freedom that live along the dotted line. And that in that description, we get the pure state. And that's maybe the reason why we think that we will get the pure state. But that relies on a conjecture, which is that the whole region behind this purple line can be replaced indeed by some degrees of freedom that live here. That was this, that was part of that sort of central dogma, right? That was this assumption.
So then it seems the outcome, so Ahmed was talking about doing a complicated experiment at very late times, which could in principle extract some information from this region in the interior. That seems to refer to what Juan, you called a moment ago, this approximate state, which has the high entanglement, and not to the exact state, which would be really a pure state. Did I understand that correctly? I mean, operationally, one could imagine doing that thought experiment, and that would distinguish between the approximate state and the pure state.
Could you say again what the thought experiment was?
Well, Ahmed should elaborate, but Ahmed was referring to some work, I think he said it was by one of the Stanford collaborations, which considered a complicated experiment at late times far from, in the radiation, which could be after the evaporation had finished, which could extract some information which in some description was still inside the interior.
Right.
So that will be true only in the situation when there was a high entanglement which remained. if the final state of the radiation in the true description is just pure, then all the information is there outside anyway.
Yeah, so you have two options somehow. If you're given the pure state, okay, you just use that pure state and you get some whatever information you want. But the idea is that if you have a situation like this one, you can do a gravity computation, right? You can do a very complicated, if you wish, gravity computation, and that computation using the gravity rules also extracts the information that naively was behind the interior, or in this other, let's say, little closed universe, and it manages to extract through a process which morally is similar to the teleportation discussion.
I see. Okay, so if you work in the approximate description, you have this interior which is left there. You have this teleportation kind of physics, and then the expectation is that someone in the final fundamental